We are a way for the cosmos to know itself. That's Carl Sagan. Pretty profound, right?
It really is. Captures that sense of wonder perfectly.
And that wonder is what fuels us here on the Deep Dive. Welcome, everyone.
Welcome. Yeah, we're here to sift through the information overload, basically. We take the source material, articles, studies, notes you might have, and pull out the key stuff.
The core insights, the need-to-know facts. Think of it as your essential briefing. We give you the context, the surprising details, so you really understand the topic.
Get you up to speed quickly.
Exactly. And today, wow, we're tackling a huge one. The origin of, well, everything. The universe itself.
We've been looking at some really interesting sources. There's a recent study in Physical Review D, and also a great essay in The Conversation by a cosmologist named Enrique Gaztañaga.
And these sources, they don't just cover the standard explanation of the Big Bang we all learned about. They introduce something, well, pretty radical.
Oh yeah, a really different take on how it all might have started, challenges some fundamental ideas.
So that's our mission for this deep dive. Unpack this new perspective. What exactly is it saying? How does it compare to the standard model?
And why should you care? Well, look, if you need to stay current on the big science questions.
Maybe you're an aspirant for exams, like the UPSC. Science and tech debates are crucial there, prelims and mains.
Definitely. Or maybe you're just curious about, existence.
Right. This is about the cutting edge.
Yeah.
Where science is right now, asking the biggest questions.
It shows that science is always moving, always questioning. It's not just a set of facts in a textbook.
Okay, let's get into it. The standard model of cosmology. For decades, this has been the champion explanation.
Based on the Big Bang Theory, yeah. The idea is the universe started as this incredibly hot, dense point, a singularity.
And then boom, rapid expansion, creating space, time, everything.
And it's been incredibly successful. I mean, it explains so much. The background radiation left over from the early universe, the way galaxies are spread out.
Loads of observational evidence supports it.
But. And there's always a but in science, isn't there? Hey, usually. Yeah. Even the best models have, let's say, fuzzy areas. The sources we looked at really highlight these puzzles, sort of holes you could poke in the standard story.
Okay, so what are some of the big ones? Where does the standard model get a bit shaky?
Well, one huge one is the matter-antimatter problem.
Ah, right. Physics suggests they should have been created in equal amounts back then.
Exactly. In the very beginning, equal matter, equal antimatter. But if that happened, they should have wiped each other out almost completely.
Leaving behind mostly energy, light, not much else.
Right. Maybe some tiny remnants. But we live in a universe that's overwhelmingly matter. Planets, stars, us. Where did all this stuff come from? Why wasn't it annihilated?
The standard model doesn't have a simple answer for that imbalance.
It struggles, yeah. That often needs to bring in some hypothetical processes we haven't actually seen yet.
Okay, what else? You mentioned inflation earlier.
Cosmic inflation, another big puzzle. The idea is that for a tiny, tiny fraction of a second, right at the start, the universe expanded. Well, faster than the speed of light.
Faster than light. Okay, that already sounds weird.
It does. And then it just stopped expanding that fast. It helps explain why the universe looks so smooth and uniform on large scales, but
why did it happen? And why did it stop?
Exactly. We don't really know the underlying physics. It feels a bit like a patch added onto the theory because it makes the math work out. What drove it? What turned it off? Big questions.
And there's a newer problem too, right? Something about measuring the expansion now.
Uh-huh. The Hubble tension. This is a really fascinating one. Depending on how you measure the current rate of the universe's expansion, you get slightly different answers.
How different?
Different enough that it's becoming statistically significant as our measurements get better. If you look at the leftover light from the early universe, you get one number. If you measure distances to nearby galaxies, you get another.
So either our measurements are wrong somewhere,
or maybe the standard model itself is missing a piece of the puzzle about how the universe's expansion has changed over time. It's a growing tension in cosmology.
And according to Gaztanaga's essay, perhaps the biggest issue is the starting point itself, that singularity.
Yeah, he makes a strong point there, an infinitely dense point.
Yeah.
It's not just immensely unsatisfying, as he puts it. It's literally where our known laws of physics completely break down.
Like, the equations just go to infinity and stop making sense.
Precisely. We can't describe it. It's like a warning sign from the math saying we don't understand what's happening here. It feels more like a limit to our theory than the actual beginning.
A boundary we can't see past.
You got it. And that leads into another criticism Gaztanaga touches on: dark energy.
The mystery force pushing the universe apart faster and faster today.
That's the one. It's supposed to make up, what, almost 70% of everything in the universe?
A huge chunk.
Yeah, but we have zero direct evidence of what it is. We only infer its existence because we see the universe's expansion accelerating.
So it's a placeholder almost. Something needed to make the observations fit the model.
You could say that. And because it's so dominant yet so mysterious, some scientists, like Gaztanaga, start to wonder, maybe we're attributing the acceleration to the wrong thing. Maybe it's not some weird energy field, but something else baked into the universe's dynamics.
Okay, so we have these gaps.
Oh.
Matter asymmetry, inflation's mystery, the Hubble tension, the singularity problem, dark energy. Quite a list.
It is. And this is where that radical alternative comes onto the stage. Black hole cosmology.
Right. This isn't totally new, but Gaztanaga's team has a specific new model.
They do. A model published in Physical Review D that they argue can actually address some of these very puzzles.
And the headline idea is, well, it's pretty wild. The Big Bang didn't just happen. It should happen inside a black hole.
That's the core of it. And that black hole formed inside a larger, older parent universe.
So like cosmic nesting dolls.
Sort of, yeah. Our universe isn't the ultimate beginning, but maybe just one event inside a much larger structure.
Which leads to that crazy thought.
Yeah.
We could be living inside a black hole right now. Everything you, me, the Earth, the stars.
Inside what we usually think of as a point of infinite density and destruction, it completely flips the script on black holes. Maybe they aren't just endpoints. Maybe they're origins.
Okay, my brain hurts a little. How does that even work? How does a collapsing black hole in universe A lead to our universe B and solve those problems like inflation and dark energy?
This is where Gaztanaga's team's specific contribution comes in. Their model focuses on something they call the bounce.
A bounce.
Yeah. Their central claim is the Big Bang wasn't the start. It was the result of something collapsing first. Imagine a huge cloud of matter or a massive star in that parent universe collapsing under gravity.
Forming a black hole, like usual.
Right. But then, inside that forming black hole, their math suggests something different happens than the standard picture.
Not different how? Doesn't stuff just get crushed into the singularity?
That's the standard view from general relativity, yes. But their calculations, the ones in the Physical Review D paper, argue it doesn't have to end in an infinitely dense point.
Why not? What stops it?
They propose that as the collapse gets incredibly intense, approaching where the singularity would form, the actual geometry of space-time behaves differently. It doesn't just shrink to zero. It changes in a very specific, rapid, nonlinear way. They call it hyperbolic.
So it kind of swerves at the last moment. Avoids hitting actual infinity.
That's a good way to put it. It avoids the infinite crush. The collapse halts. And then, crucially, it reverses. It bounces back outward.
The collapse turns into an explosion.
Into a rapid expansion, yeah. That moment of reversal, the bounce, is effectively the Big Bang in their model.
And what comes out of this bounce?
According to their math, what emerges is, and I quote, a universe remarkably like our own. Hot, dense, expanding rapidly.
Okay, that's a huge claim. But does it help with those puzzles we talked about? Inflation, dark energy.
This is where it gets really interesting. Their model suggests that the physics of the bounce itself naturally produces two distinct phases of accelerated expansion.
Two phases.
Like an initial, extremely rapid phase right after the bounce mimicking cosmic inflation, and then a later, slower phase of acceleration mimicking the effect we currently attribute to dark energy.
Whoa. So you're saying the bounce causes both inflation and dark energy-like effects without needing extra ingredients?
That's their argument. It's not driven by some unknown inflaton field or mysterious dark energy fluid. It's supposedly an inherent consequence of matter undergoing that extreme gravitational collapse and rebound. The dynamics of the bounce do the work.
If that holds up, that's incredibly elegant. It potentially solves two massive mysteries with one mechanism.
It would be a major simplification, yeah. No need to invent hypothetical stuff that makes up 95% of the universe, but we can't detect.
But there's always a but.
Always a but. As the sources emphasize, this is a very bold claim.
And the main hurdle.
The main hurdle is that it requires essentially rewriting, or discounting, as they say, some very well-established physics about singularities. Our current understanding of gravity in extreme conditions, based on general relativity, strongly points towards singularities forming in black holes.
Challenging that is a big deal.
It's huge. The standard model, with all its puzzles, is still dominant for a reason. It explains so much data incredibly well. Overthrowing it requires extraordinary evidence.
As Gaztanaga himself seemed to acknowledge, it'll take a lot more than just this model. More theory, more tests.
Absolutely. It's a fascinating, potentially revolutionary idea, but it's still on the fringes. It needs to be rigorously tested against observations and make unique, verifiable predictions.
Is there any way to test it? Are there observations we could make?
Well, Gaztanaga is hopeful. He points towards future missions, like the European Space Agency's Arakius mission.
Arakius. What does that do?
It's designed to study dark matter by looking at the very faint halos of it around galaxies. Really detailed mapping of cosmic structure.
Okay, but how does mapping dark matter help test a theory about a bounce inside a black hole?
Because different origin stories for the universe, the standard Big Bang versus a bounce model, might predict subtle differences in how matter, including dark matter, clumped together in the very early universe.
Ah, so the large-scale pattern of dark matter structures could hold clues about the initial conditions.
Potentially,
Yeah.
yes. Arakaki and other future surveys looking at the cosmic microwave background or galaxy distribution with extreme precision might find patterns or anomalies that fit one model better than the other. It's how these big theoretical ideas eventually meet the real world.
Right. So bringing this back to you, the listener, why spend time thinking about these, frankly, quite abstract and challenging ideas? What's the value?
Well, first off, it shows you where the edge of our knowledge actually is. You see that even our best scientific theories, like the Big Bang, have limits and open questions. That's where the exciting new science happens.
It also really pushes critical thinking, doesn't it? Questioning fundamental assumptions, weighing different kinds of evidence. It reminds you that science isn't just facts. It's a dynamic process of discovery and debate.
And practically speaking, like I said, for anyone needing broad general knowledge, maybe especially for exams like UPSC.
Yeah, understanding current scientific debates like this one standard model versus alternatives, the puzzles like dark energy, that's really valuable context for science and technology topics. It shows you're aware of ongoing research.
It's about appreciating that the story of the universe is still being written. We're actively trying to figure out the very beginning.
So quite a journey we've taken, from the standard Big Bang, with its incredible successes but also its nagging puzzles,
Like matter asymmetry, inflation, Hubble tension, dark energy.
to this really provocative alternative, black hole cosmology, where our universe might be the outcome of the bounce inside a black hole from a parent universe.
A model that potentially offers neat solutions for inflation and dark energy, deriving them from the bounce dynamics itself.
But one that faces the major challenge of needing to revise core physics and requires much more evidence.
Exactly. The standard model reigns for now, but the questions remain. And ideas like the bounce keep pushing the boundaries.
Which leaves us with a final thought to chew on, stemming from this bounce idea. If our universe is one bounce, could there be others? Could we be part of an endless cycle, a cosmic foam of universes bouncing in and out of existence within some larger structure?
Or is the standard Big Bang, singularity and all, the one true story? The quest for answers continues.
It's definitely humbling to think about. We really hope this deep dive has sparked your curiosity and given you some clear takeaways from the source material on this cosmic debate. Thanks so much for joining us.
Yeah, thanks for exploring these huge questions with us.
If you found this interesting and you want more deep dives that cut through the complexity, please do like this and subscribe to the deep dive. It really helps us keep doing this.
And please, leave comments. Any questions about cosmology, the bounce, the standard model, or ideas for future topics, let us know.
We'd love to hear from you. Until next time on The Deep Dive.